Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside. I want to check on and see if you are ready for the Chapter 9 stuff on right triangles and trigonometry. I got a review for you with a packet description section down below. You can go download this thing and find the timestamps to the respective sections and the problems associated with those sections. It's 7 pages long. I don't know how many questions overall because there are some numbers with parts and the numbers reset every time we go into another section. We've done several of these. I think it's the 4th one we've done since chapter 6. So are you ready? Let's go ahead and find out. Grab a calculator because you're going to need it, especially for the trig parts. I like how it just starts with "Are you ready?" at the top. Are you ready? We'll find out. Excuse me. All right. Lesson 9.1 on Pythagorean theorem. There are some different kinds of questions we'll have, including the general old a squared plus b squared equals c squared bit. In any right triangle, this is a true statement, where a and b would be the legs of your right triangle, c would be the hypotenuse. Doesn't matter which order a and b is in, as long as c is the longest guy. So, solve for the missing side. If I have legs of 8 and 13, I need to find the hypotenuse x. My setup is 8 squared plus 13 squared equals x squared. Already feeling like I may need the calculator depending on what I'm going to do here. 13 squared is 169. 169. And not combine like terms, add these together, we get 233. Ooh, I don't know if that has a square root of 233 at the very least. I don't know if that has any sort of perfect square factors in it. Let's see. It cannot divide by 9. My question is, let's see. I need to see if I can factor out I can't do an even number. Can't do a factor of 5. Does 49 work? No. That is, to my knowledge, no. No, it shouldn't. I don't know. I almost want to pause the video and think about it. Let's see. 81. No, 243 would be there. So not quite. I don't think anything goes in there. We'll just say square root of 233. If we had an approximated value, it would be somewhere a little more than 15. Probably 15.4. I don't know exactly. All right, that's the first part. See, number 1 has 3 parts in and of itself. This one here, don't think of x as the hypotenuse because it ain't. Just because it's slanted. I mean, these are all slanted, right? It doesn't matter. What matters is what's opposite the right angle. That's the hypotenuse right there. So when we're solving this thing, x is a leg. X squared plus 9.2 squared equals 16.5 squared. That's what we're going off of this time. And I'm going to go ahead and do a couple things. I'm going to change the color. I'm going to get my calculator ready because I don't know these numbers squared for the life of me. This is one of those where maybe it's probably better served that I just round my answer ultimately, but let's see what 9.2 squared is. I'm getting 84.64. So x squared plus 84.64, and here's 16.5 squared. 272.25. 272.25. I'm very curious to see what this guy's square root is going to look like. X squared. Let's subtract that. I don't trust myself with subtraction these days. 187.61. So x would be the square root of this. Let's see what that square root is to begin with. It's not a perfect number. Like, it's an irrational value. So I'll start with just the square root of 187.61. That's as exact as it'd get without, like, I can't simplify that one to my knowledge. And so it's around 13.70. I'll use 2 decimal places rounded. It would be around that or that there. So either or, it applies. We get one or the other. So not perfect values, not Pythagorean triples either. I've been mentioning Pythagorean triples in the past, and these are not all rational value sets. So not super clean. This third one we got to solve for x, and if you notice that x is over here, one of the legs of this right triangle, where the hypotenuse is known, but that leg's not known. So we got to find that leg. But this is a leg, I'm going to call this temporarily y. This is a leg right here, y, that seems like I need to find first. And I need to find it with this right triangle right here. So this one in green has a hypotenuse of 25, one of the legs of 16. We got to find y given that. So let's, I said green, I'm going to use purple. Let's use y squared plus 16 squared equals 25 squared. Now 16 and 25 themselves are perfect squares, but that's not the point. We are squaring them. We get 256, and here's 625. And that is, again, not trusting my own math here, 369, 372. 625 minus 256. 369. 369. And I've seen that number before on problems enough that we did something by taking a square root of it somewhere. It's not a perfect square, but like a 9 can divide out. It's 9 and 41, I think. So it's 3 root 41, square root of 9 times square root of 41. Now that 3 root 41, here's the thing. Honestly, I don't even need to take the square root. Let me backtrack one step. Y isn't what I need to solve for. X is what I need to solve for. To solve for X, I need to use Pythagorean theorem with these things. So even though Y is the square root of 369, the only thing I really need, sorry that there's like a seizure thing going on in the background. Even though Y is something that I need as a whole, I really need Y squared, right? The whole thing here is going to be X squared plus Y squared equals 22. 22 being the hypotenuse here. Y squared is what I need, the 369. So let's just go off that, 22 squared, excuse me. So X squared plus 369 equals, I think that's 484, and this is where I go to work. So X squared equals, let's see, 484 minus 369. 115, and X is the square root of 115. Also, I don't believe that one can simplify as a radical. So not clean answers, but exact answers were had, and we found incorrect answers, mind you. All right, let's keep moving forward. Let's take a look at number 2. A 31-foot support wire is attached from the top of a 25-foot telephone pole to a point on the ground. How far from the base of the pole does the wire meet the ground? So this is a word problem, but still has Pythagorean theorem basis to it. So I have a 31-foot support wire, 25-foot telephone pole. Here's the support wire right here. So 31 feet of a support wire to a telephone pole up here that's 25 feet. They want to find how far from the ground, how far from the base of the pole does the wire meet the ground. So here's the wire meeting the ground, here's the base of the pole. So here's our unknown. Our answer will be in feet, but we'll go X squared plus 25 squared equals 31 squared. This one I'm going to round my answer. You know, being a word problem, we want to say things with feet there. We'll get there. So X squared plus 625 equals, I should know 31 squared, 961? 31 squared. 961, okay. Only problem is I don't know the subtraction. I do, I just don't want to spend time doing it. And that one would be right. 336. So X squared equals 336. I'm just going to go for the square root, the rounded to the nearest 10th answer immediately, instead of trying to get like an exact simplified answer. Around 18.3. 18.3 feet is this answer here. So clearly my thing isn't very drawn to scale because 18.3 looks longer than 25. But that would be the ultimate result for that guy. All right, number 3 has 4 parts to them, A, B, C, D. Determine whether the triangle with the given side lengths is acute, right, or obtuse, or not a triangle. And that's actually a good point that we have to make with these ones here is, do we make a triangle to begin with? This goes back to, I don't know, I think it's chapter 6. Might have been chapter 6 where we did the triangle inequality theorem, where these side lengths go up, they increase in order, so it's really easy to check and see. We want to know if the 2 shortest lengths added together are greater than the third length. Does 11 plus 13 exceed 35? That's always the thing in question. Let me actually just write it over here and do these parts. So part A. Does 11 plus 13 exceed 35? Well, 11 plus 13 is 24. 24 is not greater than 35. On part A, that is not a triangle. Now, that's the first time that we've run across, not in total, but in this chapter, when I've done problems, the first time we've run across one that wasn't just a triangle, period. You don't do the test to say acute, right, obtuse if it's not a triangle to begin with. And that is such the case here. So part A, not even a triangle. They need to exceed that. A plus B must be greater than C. Part B, now 9 plus 15. Is 9 plus 15 greater than 19? It's almost one of those things where like, yeah, 24 is greater than 19, so it's a triangle. But is it acute, right, or obtuse? We know in a right triangle, a squared plus b squared equals c squared. But also conversely, in a triangle, if a squared plus b squared equals c squared, then it is a right triangle. If a squared plus b squared is greater than c squared, let me write these down. If a squared plus b squared equals c squared, we have a right triangle. But if a squared plus b squared is greater than c squared, we have an acute triangle. It's that A and B are long enough that they dominate C's length so that they're actually not a right angle they have to bend in. But if A squared plus B squared is less than C squared, we have an obtuse triangle. Now, remember, A plus B must be greater than C. A plus B is greater than C must be true. So don't forget that part, that we have to first kind of give that test. So let's go ahead and see if 9 squared plus 15 squared is, how does it compare to 19 squared, basically? 9 squared plus 15 squared, greater than, equal to, less than. So 9 squared is 81, 15 squared is 225. Not much room for these problems here. I will have room to scroll down, just if you're doing these problems, you really got to squeeze this stuff in. 19 squared. 361? Wait, hold on. Did we just do that? No, we did something else. But yeah, 361. 361, and that is not quite there. That's 306. And that is less than 361. So A squared plus B squared is less than C squared. This is an obtuse triangle. It is a triangle, but it is obtuse. Part C. We know 21 plus 28 is greater than 35. I'm going to go ahead and move forward there, but always do that test. And notice that I am doing, keep writing plus there. Notice that I am testing the two smaller sides as my A and B. These are written in order, which I guess is a blessing, but if they were written out of order, the C that we're testing against, that's potentially your hypotenuse or whatever, it's got to be your longest side. Right? That's the only way to make that true determination of what this thing is, if it's a right triangle or otherwise. Otherwise, your answer will always be acute, which is not always the case. This is 441. I don't know 28 squared. 28. I don't even want to guess. 784. And I believe 35 squared is 1225. So I'll go with that. 441. Oh, I think this is this is a 345 Pythagorean triple, isn't it? Yes. So 1225. I should have seen that off the bat. 1225 and 1225. These are equal to each other. So this is a right triangle. Yes, this is one of the 345 Pythagorean triples. 21 is 7 times larger than 3. 28 is 7 times larger than 4, and 35 is 7 times larger than 5. That's one of the ones that would make a right triangle. All right, the last one I want to do here, 8, 12, and 14. We know 8 plus 12 is greater than 14, so let's go ahead and check these out. It's not a Pythagorean triple. Hoping to get an acute answer just for diversity's sake, but I'll take what I get. How does it compare to 14 squared? We got 64, 144, and 196. Oh yeah, this will be greater than. But finish it. 208. This is greater than 196. A squared plus B squared is greater than C squared. This triangle is acute, and it is indeed a triangle. So you get each type of answer provided here. What we didn't get, and I was going to do, if you recall back to this problem with y squared, I was going to say that y is 9 root 41, right? Y is 9 root 41. And then I was going to go back and say, now we got to square it. But I was like, oh, we already have that squared. Excuse me, 3 root 41. 3 root 41. The point I'm going to make is that we didn't get to practice squaring one of these. You square one of these by squaring, y squared. You square 3 to get 9. You square root 41 to get 41. And 9 times 41 is 369. But we didn't get one of those to do a comparison thing with, but that's okay. Every answer was diverse. All right, that was your section 9.1. Let's move to section 9.2, which has two basic natures of special right triangles. We got the classic 45, 45, 90 special right triangle, which has a 1-to-1 to root 2 ratio relationship, which means each leg is equal in length and the hypotenuse is root 2 times larger than either leg. You also have the 30, 60, 90 triangle, where opposite the 30 is going to be the shortest side, if we call that 1. Then opposite the, the hypotenuse is the 2, that's the longest side, and then root 3 is opposite the long leg right there. So compared to the short side, the hypotenuse is twice as long, and compared to the short leg, the long leg is root 3 times as long. Now, other teachers often just use the x's. They'll say x, x, and x root 2. That's fine. It's probably more proper in x, 2x, and x root 3 like that. I just stay away from them just by saying numbers. It's a little cleaner. 1-to-1 to root 2, x, x to x root 2 is kind of weird. Point is, these are all similar to each other. All 30, 60, 90 triangles are similar by angle, angle. Therefore, this will always apply. The hypotenuse is always twice as long as the short leg, things like that. So let's go and kick that off. Let's look at this part A. Find the missing side lengths. Leave your answers as radicals in simplest form. I'm going to stay away from the calculator completely. this time. There's nothing I have to use for it, to my knowledge. This is a hypotenuse in a 30, 60, 90 triangle, and opposite the 30 is the short leg, which should be twice as small as the hypotenuse. So I need to take this hypotenuse here and divide it by 2. That'll get me this guy. So x is 32 over 2, which is 16. That is x's length. Let me even change that to a 16 itself. Y is the long leg. Compared to the short leg, it's root 3 times larger. So y is 16 times root 3. That is simplest radical form. That is the answer for y. It's 16 root 3. B and C are also 30, 60, 90 triangles. Looks like we hit the 45s after that. So let's continue forward. Now we have the long leg as 5. This one can get a little tricky. I do want to solve for y first. As you notice, we kind of traverse to the short leg before we get to the hypotenuse. We'll divide this by root 3 to get short leg. We'll multiply this by 2 to get hypotenuse. That's the easy part. Dividing by root 3 can be tricky because they say simplest form. Leave your answers radicals in simplest form. So 5 over root 3 is not enough. We don't finish on that part of the problem. We have to multiply top and bottom by root 3 to rationalize the denominator. And that becomes 5 root 3 over 3, which cannot simplify further. If this was like 6 root 3 over 3, then I would do 6 over 3, make it 2, something like that. But we're going to leave this as is. That'll be my final result for y. And you could write it like that if you want. Just remember that y is this value because x is based on y. X is taking 5 root 3 over 3 and doubling it times 2. What do you multiply by 2? Just the 5. It's the only numerator value. It's outside of a radical, things like that. This is 10 root 3 over 3. Sorry, let me get that out of the way. And that is your final set and result. They're not pretty, but they are simplified. They are correct. We finish off that. Part C is more of that. It is, once again, and I didn't mention this was a 30 here, but clearly if the other's 60, that's going to be 30. This is another 30, 60, 90 in the same exact vein. We are at the side opposite the 60, and we got to get to the short one. We will divide by root 3, indeed, and then we are going to multiply by 2 going this way. So we start by getting B. B is 3 root 2 over root 3. This once again must rationalize, and we get 3, root 2 times root 3 is root 6, and root 3 times root 3 is 3, so that's gone, that's there, and 3 over 3 makes those go away, right? 3 over 3 is 1, so you're just left with root 6. So B is root 6, that's the end result of B. Let me move that over a little bit. That's as clean as we can get, and I'll leave it. A, I was looking at the letter. I'm like, how do I say that? A is root 6 times 2. Does that make it root 12? No, it makes it 2 root 6. Root 12 would be root 2 times root 6. I wanted to just box this guy. And if it was root 12, I'd have to simplify it because it has a perfect square of 4. But this does not here. All right, let's go to parts D and E, where our 45, 45, 90 triangles exist. So like that would be a 45, for example. I got a 3 root 6 here. Now, these have the 1-to-1 to root 2 ratio relationship, which means these guys are equal to each other. I'm going to straight up just tell you guys, B is 3 root 6. Easiest answer you can get, assuming you know how that thing works out. Now this, we got to multiply by the square root of 2. I think we just came off of a question where I had root 6 times 2. I said it was 2 root 6. 3 root 6 times root 2. However, this is where the radical gets affected. 3 root 6 times root 2 is 3 root 12. I was just bringing this up. 12 is not simplified. Root 12 is not simplified. Square root of 4 exists inside of here. Root 12 equals root 4 times root 3, which is 2 root 3. So we're going to do 3 times 2 root 3, which is 6 root 3. So interestingly enough, we go from 3 root 6 here to 6 root 3 here. And yes, 6 root 3 is bigger than 3 root 6. It's root 2 times bigger, in fact. And those are the simplified results of B and A. Part E. We have 3 root 3 as the hypotenuse in the 45, 45, 90 triangle. Whatever S is, R is. Okay, you're going to get the same answer for both because they are equal in length. So we are going to have to divide by root 2 to get there, though. And like I said, these are equal. So I'm just going to write it like this. Like S equals R, which equals whatever. They're both the same answer. We got to take 3 root 3 and divide it by root 2. To rationalize this denominator, we'll multiply top and bottom by root 2, and we will get 3 root 6 all over 2, and that's as clean as we can get. Both S and R have that length exactly. Okay, so like I said, stay away from the calculator with these things. Always simplify the radicals and get to that form. Whether you like the look or not isn't your decision to make on whether it's simplified, right? Rationalize the denominator, we're good to go. You can see when it helps. You can see when it doesn't help. But regardless, that's what we get. Now, F and G have an interesting look to them. They remind me of what we did on that one Pythagorean theorem question where two things were attached. We got to solve for x, but in order to do that, we have to find out more information inside this triangle. But this triangle shares a hypotenuse here with the short leg of the 30, 60, 90 triangle. So let me actually color code this thing. I'll go ahead and go in green on the 30, 60, 90 triangle. As you can see, I will not really need this value. That's not really needed. I really just need this value here. And like before, I'll just call it y. This is the hypotenuse of your 30, 60, 90 triangle. Opposite the 30 should be twice as small. Y is 8 root 3 over 2, which is 4 root 3. That is this guy. So I'm going to go ahead and put that in. I got 4 root 3. 4 root 3 now exists as the hypotenuse in the 45, 45, 90 triangle, which is root 2 times larger than either leg. X takes 4 root 3, and we have to divide that by root 2. And we just did something like that right here. 3 root 3 divided by root 2. So this is going to look very similar, but something's going to clean up a little more, which is nice. This becomes 4 root 6 all over 2, and 4 over 2 is 2. So you get 2 root 6. Like I said, simplifying sometimes does have its uses and benefits, and this is one of the cases where it looks a little bit better than maybe it did to begin with. So 2 root 6 is the answer for x. That's what we needed to solve. We got it. We're good. Let's go to G. G, same thing. We got to get a leg from this short side that we have. This is a 30, 60, 90 right here in, let's say, purple. And let's go ahead and attack the blue afterward. We got to get, once again, the hypotenuse of the 45, 45, 90. To get that, it is the long leg of the purple. We start with the short leg of 6. I'm going to call that y again. Y is 6 times root 3. I mean, straightforward. That's what it is. You know, this 1 to 2 to root 3 ratio relationship, this being the root 3 is there. And, you know, I didn't bring this up. I mentioned that 2 is longer than root 3. Sometimes people confuse that. They think root 3 is longer than 2, so they put it here. I just want to state that one way to remember that root 3 is less than 2 is because 2 is also the square root of 4. Square root of 4 is more than the square root of 3. So keep in mind, hypotenuse always has to be the longest length, and that root 3 is for the long leg of the 30, 60, 90 triangle, not the hypotenuse. All right, 6 root 3. This also is the hypotenuse of this guy here, and looks like we're going to have a very similar S concept. We got to divide this by root 2, 6 root 3 over root 2, to get the legs of the 45, 45, 90 triangle, either or. So, not equals. Let's rationalize that once again. This will look very, very similar to the ones we just had. So root 2 over root 2, and we're going to get 6 root 6 over 2. 6 over 2 is 3, and we get 3 root 6. And that's the final answer for x. So those interconnect. They have their purposes. Hopefully we led those through just fine. I got it. Give me one moment as I correct this one. All right, let's go to 9.3. Similar right triangles. Using right triangle similarity theorem, solve for x. Now, I don't remember the theorem by name. I just know that people talk about this differently. So I'm going to cater to almost every version that I can come up with. I think I have the capability of doing so. I'm going to start off with, what if you came up with which triangles were similar to each other? Maybe by redrawing them. And what I mean by that is, let's say, you know, I have this, the biggest right triangle here. The biggest right triangle here is triangle ABC. If I reorient it so that it's drawn this way, notice that B is the right angle in the big, I'm just going to call it the big triangle. The big triangle B is right here. Then you have the short leg A. Yes, I didn't just rotate it. I also kind of reflected it across. From B to C is kind of that long leg. We're going based off visuals, but this will also be true. That'll be the long leg there. And that's the big triangle. Now, within here, we can fill out some information. We'll do that in just a moment. Let's go to what essentially would be the medium triangle. It's this guy right here. It's the second smallest in size. And I can just kind of bring that over now. It looks like this guy. This has a right angle here at D, right? This is the altitude here, and that's D being the right angle, and then the short leg up to B, and the long leg from D to C. Then we have the small triangle. Let's do that again. We have the small triangle over here. The right angle is once again D, and then we have A up to the short side, and to the long side we got B, representing the hypotenuse. That is a small. Now, I probably don't plan on doing redraws after this. What you're going to hear me say a lot of, instead of saying redraw, is I'll be mentioning these as big, medium, and small triangles. I'll be talking about long legs, short legs, and hypotenuses of each of them. But what's nice about doing this is you can see clearly triangle ABC is similar to triangle BDC, which is similar to triangle ADB. Now, this may not be, I don't know if it is, this may or may not be the right triangle similarity theorem, but this is a similar triangles proposition that I'm going to form here. That when you have similar triangles and all three are similar, yeah, corresponding angles are congruent, but corresponding sides are proportional. Now, the reason that these are congruent is by angle, so I'm not busy with that. I want to talk about the proportionality of these. So what I want to do now with this redraw is label parts that I can find. Clearly in the medium triangle, this length is 4, this length is x. 4, x. And in the small triangle, if you see that it kind of rotated downward there, we have the long leg of 4 and the short leg of 2. These parts correspond, this 2 and this 4, and this x. See, in the big triangle, my short leg is unknown. Could I use Pythagorean theorem to get it? Yes, I could. The long leg is unknown as well. The hypotenuse, in a way, is known. It's a combination of 2 and x, that entire length. Let's call that thing x plus 2. Now, the other reason, I can use this, even though I'm not going to use this method anymore of redraws, I can use this method to explain what I'll be doing later. The parts that correspond that I can use are in both the medium triangle and the small triangle. You see, this 4 shares itself with two triangles, and it's represented as two different parts in those triangles. The 4 is not only the short leg of the medium triangle, but it's also the long leg of the small triangle. So in a way, listen, the big triangle is not only, we not only don't have two parts in the big triangle, but the part that we have doesn't correspond to parts that we know in these other triangles. Yes, in the small, we could use Pythagorean theorem to get whatever this value is here, but it's irrational, and we don't have another part with big to figure out what that's going to be. I guess it would be this over here. It's just not worth our time and investment to do so. I'm going to go ahead and say that. But the medium and small triangles do have them. So, like I said, 4 is both the short leg of the medium triangle, the short of the medium, but it's also the long leg of the small triangle. Now, short leg and long leg don't correspond. So if I build a ratio here, notice that I mentioned small. I need to find the short leg of the small triangle, and I do have it, which is great. Now I need to go medium to small again when it comes to setting up a proportion. Is this the only order you can set up the proportion? Absolutely not. Not even close. We have a bunch of different ways we can vary this thing, but this is what I'm talking about. Remember, this was the long leg of the small that we have as 4. 4 represents both, and this is how you're going to say it. You said if it represents the short leg and the long leg of both the medium and small triangles, that's what we're going to use. Short of medium, short of small, long of medium, long of small. And this is where the proportion is going to set up. And I know I spent a longer time talking about this one, so I can speed up on the other ones later. That being said, the short leg of the medium is 4. The short leg of the small is 2. 4 over 2. Don't worry about calling it 2 right now. Equals long leg of the medium is x. Long leg of the small is 4. That's our proportion. That's our setup. Now I'll cross multiply. In doing so, I'm going to write it here as 4 squared equals 2 times x. I know 4 squared is 16, but I want to bring up something else as well, which is geometric means. 4 is not only just two different parts of two different triangles, it also represents the geometric mean of these two split parts of the hypotenuse of the big triangle. If 4 is the geometric mean of 2 and x, 4 is geometric mean of 2 and x, You could therefore set up this proportion like that to make it happen, and you can go straight to what the textbook often does, is brings you right to the squared portion right here, that this squared equals this times this. That's why I bring that up. That's why I bring that up. And I want to bring that up every so often with problems, but I do want to set them up with proportions to show you how it works, because all of those have some sort of geometric mean. Not all of them, but a lot of them have geometric mean setups if you look at them right. Anyway, 4 squared is 16. And divided both sides by 2, you get x equals 8. So it's the long way of talking about how to get that answer there. This was a very short way of talking about how to get the answer here. I'm going to often find the in-between, not by doing triangle redraws, but by mentioning what part I have, and do I have it represented in the rest of my triangle. That's the big aspect I want to do here. So let's move forward. Let's go to part B. And here's another set of the right triangle stuff. I got the big triangle here. I got the medium triangle here. And I got the small triangle here. Now, in my big triangle, the only thing represented truly is the hypotenuse. This kind of almost feels like the previous problem that we had. In the medium triangle, you could argue you only have the x, but with a very quick calculation, you could do 25 minus 9 and get 16 right here. So now you have 2 different aspects of that medium triangle. You have the short leg and the long leg. What's great about that is x represents also the long leg of the small triangle, and you also have the short leg of the small triangle. So I used my 25 to the extent that I need to use it. I don't need to use it truly anymore. I have enough information in my medium and small triangles to build up what I did last time. Truly, x being the geometric mean of 16 and 9. X represents the short leg in the small triangle. 9 represents the short leg. Sorry, in the medium triangle. 9 represents the short leg in the small triangle. Did I say medium small? Let's go medium small again. Long leg of the medium triangle is 16. Long leg of the small triangle is x. When I cross multiply, I get x squared is 16 times 9. X is truly the geometric mean of 16 and 9. And if you knew that, you could go straight into this part right here. This is kind of a geometric mean theorem that we get to. You could do 16 times 9. You could also do a square root at this stage. I want to show you this in case you haven't done this before. You do root 16 times root 9, right? Root 16 is 4, root 9 is 3, and 4 times 3 is 12. So if you didn't want to go with 16 by 9, go smaller first if you want, and you can take care of it. When it's a perfect square, it works out even better. Part C, this one's represented a little different. This time we don't have this altitude, which means we don't have a connection of the long leg of the small and the short leg of the medium or anything like that. But this x right here does happen to represent 2 different parts of 2 different triangles. X is the short leg of the big, but it's also the hypotenuse of the small triangle. That means I want to find corresponding parts short of the small, and I want to find hypotenuse of big. Let's see if we have those, or we can generate those for ourselves in some sort of way. So let's talk about the short leg of the big triangle, x, over, let's go the short leg of the small triangle. That would have been here. I don't have that. Ooh, but I can get that. 12 minus 7, I get 5. Short leg of the small. So short of big over short of small equals, now go big over small again, hypotenuses. Hypotenuse of big, 12, over hypotenuse of small, x. Notice, I don't use the 7 anymore. I'm not erasing it like it's gone, like it was irrelevant to the problem. I'm just not using it anymore for the rest of the problem. Cross multiply here, we get x squared equals 12 times 5. This time I'll put 60. And let's take the square root. Oh, by the way, this is where, let me mention this. As far as geometric mean goes, last time we said this altitude was the geometric mean of this part and this part, right? Which is true. This time, this guy right here is the geometric mean of 5 and 12 of, I don't know how to say it best, but this squared equals this times this. That's why I'm not really talking about those, but that's what we brought up. 12 times 5, or 5 times 12. 5 times 12. X squared equals 5 times 12. Anyway, let's take the square root of both parts here, and we get square root of 60 is root 4 times root 15, so I get 2 root 15. Did they ever say answers? They just said solve for x, so that's an exact answer there. We're good on C. Now, part D is three variables to solve for. Let's see where we want to work this thing out first. Just kind of dance around this thing as best you can. Do you automatically go straight for these like theorems and you do proportions and stuff? Not necessarily. When I look at y, I look at it as the third side not known in this right triangle, where I can use Pythagorean theorem to find y. That seems like a good place I can just kind of jump to, right? This is a right angle right here. So I'm going to start Pythagorean theorem. There might be other ways to start it. This is just the first thing that I see. So I'm going to go straight to it. Y squared plus 24 squared is 27 squared. I'll need the calculator briefly. But 576. I don't know 27 squared, though. If I had to make a guess, I don't have a guess. 709. 27 squared is 729. Actually, I should have known that. Sorry. There are reasons I should have known that. Other math teachers will shake their head. Y squared is 153. So y is the square root of 153. And in all honesty, I don't... That does simplify. 9. 9 and 17. So 3 root 17 is that result. Wow. I was going to say that looks like a prime number. It's not a prime number. That can divide by 9. So 3 root 17 is that y value. And I'm going to go ahead and replace that because I'm probably going to use that, right? That'll probably be used. Not only that, I might end up using y squared at some points. This is one of those altitudes here, so it's something that'll probably be used in that way, which is nice. Okay, now I have more information that's truly helpful to my cause. I have this 3 root 17, which represents both the short leg of the medium triangle and the long leg of the small triangle. I think this is a good case where I can come up with, I think x. You know, here's the thing. Even though x represents this whole guy right here, this would also be x minus 24 right there. The whole thing's x. Take this 24 away, and you have this. And I bring that up because I think x is my next go-to for solving. I think if I solve for z, I got to somehow use x. So I think x comes next. 3 root 17, again, the short leg of the medium over the short leg of the small equals the long leg of the medium over the long leg of the small. Now, the 3 root 17s would cross multiply, or we cross multiply, we get 3 root 17 squared, and we've seen that before because it's 153. So let me actually change colors. All right, there, and sorry. All right, that's 153. Let's distribute. Add 153. I guess you get 729, right? 729 equals 24x. So x is 729 over 24. Now, they can divide by at least 3. You get 243 over 8. I guess that's the extent to which you can go. 243 over 8. There's an exact answer within 30.375. Let me try that. Let me try and do 729 over 24 to make sure I get that same number. 30.375. So here's an exact. I mean, they're both exact, but here's that decimal is exact. This fraction is exact and reduced. I only hope I'm doing the rest. I hope I'm doing this problem right. Otherwise, you're leading one mistake into the others. That's x. That's the whole thing, right? This is this guy 30.375 or 243 over 8. You know that biz. Solving for z now has a lot of options. I mean, a lot. You can plug in this 30. First of all, the one I'm probably going to do is you can just use the big triangle and go Pythagorean theorem on it. Okay, boom, Pythagorean theorem. This squared equals this squared plus this squared is, I guess, where I'm going to go because I got to rely on x to get z. You could also do 30.375 minus 24, get that number, and work out your triangle similarity. I kind of feel like that's what I'm supposed to be doing for this problem. I just question how in-depth the numbers are going to get. I think I'm going to lose people on this problem just by talking about it with the math because you have fractions and stuff within, but that's the nature of the problem. The thing is, I don't need the 3 root 17 though, but I could use the 3 root 17 if I set this up as the right triangle. This squared plus this squared is that squared, so that's possible. Let's stick to similarity stuff. We're in that section right now. Bear with me. Fractions are going to look weird. Now, I'm going to use the fraction version. Fractions are going to look weird on this. Let's begin with the fact that I need to figure out what 243 over 8 minus 24 is. Now, 24 times 8, I got to get a common denominator. 24 times 8 is 192. 243 over 8 minus 192 over 8, which is, let's just not mess this up, 51 over 8. 51 over 8. So that's this guy right there. So 51 over 8. Boom. Which is important because when I find z, z is both the hypotenuse of the small and the short leg of the big. It's also the geometric mean of 51 over 8 and 243 over 8, but that's neither here nor there. Hypotenuse of the small and the short leg of the big. Well, here's the short leg of the small, 51 over 8. Here's the hypotenuse of the big. Let's change that to its fraction, 243 over 8. So let's set up a proportion with that in mind. Let's go the hypotenuse of the small over the hypotenuse of the big equals the short leg of the small over the short leg of the big. And that's z. The hypotenuse of the big. Wait. No. Short leg of the big. Z. Short leg of the big. All right, when I cross multiply, I'm going to get z squared equals 243 over 8 times 51 over 8. Now, I got to take the square root at some point. I don't know if I want to do 243 times 51, though. I need to see if there's something else I can do better. The good thing is I know 64 is on the bottom. So let's just kind of keep it like that for a moment. I have some thoughts, but I want to see where I go with it. If I take the square root of both sides here, I know on the bottom I get 8. But on the top, see, 243 is 81 times 3. And that means that I'm left with root 243 as 9 root 3. So this is 9 root 3. Root 51 can be written as root 3 times root 17. That doesn't simplify anything in and of itself, but the root 3's can simplify. So instead of getting to big numbers, I'll work out these smaller numbers, and I'm going to get 9 times 3 times root 17 all over 8, which is 27 root 17 all over 8. That's an exact answer without letting the calculator do any rationalization, things like that. That's why I wanted to work out the fractions. It's a lot. There's a great chance I could have made one slight mistake somewhere. I don't know where. Maybe it was at the very beginning, but I think I let my calculator do things correctly for me there. Y was one of the things. So I'm going to trust what I have. It's just the setup of the problem. Those are the answers. Feel pretty good about it. Okay, that was 9.3 material, and that's it. Now we're going to 9.4 and 9.5 using sine, cosine, and tangent. 9.4 was strictly on tangent. 9.5 was strictly on sine and cosine. When you put them together, you get all sine, cosine, and tangent. You get SOHCAHTOA, baby. Now, people write this differently. This is how I write it. I see some people write it in a much more glorious way, like this. SOHCAHTOA. It's all about this division of these things. And I'll use this one to talk about what it is that we're doing. SOHCAHTOA is just a 9-letter word in some way to say that the sine of an angle equals its opposite over hypotenuse. The cosine of an angle is adjacent over hypotenuse. Tangent of an angle is opposite over adjacent. I'm not going to go deep into the teachings as to why. You've seen it before, hopefully. If you're on the Are You Ready portion, you just want to see if you can get the answers right. Let's go ahead and come up with what they want us to do. For number 1 and parts A and B, for each question, identify trig ratios, sine, cosine, and tangent. So theta is this angle here that we want to talk about. It's the reference angle. We want to take the sine of that angle theta. We want to take the cosine of the angle theta and tangent. So we get sine of this angle is opposite over hypotenuse. Now, opposite is in relation to the angle. Opposite theta is 12. The hypotenuse of the triangle is 13. We're good. 12/13. That's it. All of these, no fractions to reduce here. We'll just leave it. Cosine of theta, the adjacent leg is 5. It's this guy here. And the hypotenuse is 13. So 5 over 13 is this guy. And then the tangent of this angle is opposite over adjacent, 12/5. We'll leave it just like that. Fractions are perfect for these ones. That'll be it for those three. That is part A. Part B, we have the angle here with this kind of upside down right triangle. Theta is that guy. Let's take the sine of theta. Opposite this angle is 11 over the, well, not 22, over the hypotenuse of 11 root 5. Now, you don't leave this one for several reasons. Number one, the 11s they don't cancel. They become 1. And so you're left with a 1 on top and then root 5 on bottom. Second thing is we do, yes, have to rationalize this denominator. Multiply top and bottom by root 5. and you end up getting a result that looks like root 5 over 5. When you get into IM3 trig or pre-calc, you start using root 2 over 2 a lot for 45, 45, 90 triangles. And sometimes root 3 over 3. Cosine. Cosine of theta. This is the adjacent over hypotenuse. That's 22 over 11 root 5. I don't know what 11 root 5 is. I'm trusting that it's long. Well, I'm trusting through Pythagorean theorem. These are the values, in I guess. But it must be more than 22. Now, again, reduce these. That becomes 2 over root 5. When you rationalize this one, it becomes 2 root 5 over 5. Multiply top and bottom by root 5 there. You'll get that same effect. And then part C, and not part C, the tangent of theta, we do opposite over adjacent. Opposite theta is 11, and the adjacent leg is 22, and that's just 1/2. Well, that was the easy one. We should have started with that part. So yes, 1/2 is just that answer. Meanwhile, sine and cosine get a little different. All right, that is part B of number 1. Number 2, solving for sides. I forget what page we're on, but 9.6 is the last section. That's all I remember. Solving for sides. We need to find this missing x given this angle. Let's just take it for what it is, 38.9 degrees, and this 13. Now, given SOHCAHTOA, you want to think about which parts you have in relation to this angle. 13 is opposite of the angle. X is the adjacent to the angle. The O and A are tangent, TOA. So we want to use tangent here. Here's our setup. The tangent of our angle equals opposite over adjacent, 13 over x. Now, there's a two-step process in getting x by itself. You'll see me do this very fast in other problems. I'll say it this first time, and then I'll show you what to do after. So first you multiply both sides by x because you have to get x out of the denominator. That's x times the tangent of this equals 13. And then to solve for, that was thunder. And then to solve for x, it still is thunder, you have to divide both sides by tangent of 38.9. And this is the exact, this is the exact portion, 13 over tangent of 38.9. Now, I'm just going to write it one more time because that's gone here as the x's were gone here. X equals, I'll need less room for this one, 13 over tangent of 38.9 degrees. So there's an exact. We will approximate it. I'll round to the nearest tenth, if that's cool. I'll go and box this answer, though, as if an exact does matter. It matters for what you type in. But here's what I wanted to point out before I calculate. When x is in your denominator here in these ratios, it ends up just kind of swapping places with your trig function right here. X and tangent of 39 ended up taking their spots. It was here, now it's up there. This was here, now it's down there, as you can see. So you're going to see me switch places on a lot of those situations when that is relevant to the problem, and it was in this case. Now, I'm going to go to my calculator for a second with you guys here. I'm going to turn it on. This was what I was typing in before. And make sure that you are in degrees instead of radians. Your calculator probably is defaulting to that unless you're pressing some funky buttons or using a different one. Or you share your teacher, teaches IM3 or pre-calc, and they might be using radians sometimes. But we're going to do 13 over tangent of 38.9. Notice that I never rounded or calculated tangent of 38.9 until the very, very end. Don't use rounded answers ever in a problem to calculate other answers. I'm going to call it 16.1. This is the length of that side, so it's just units. That'll be its final. We're good there. Part B. I need this hypotenuse, and I have the leg adjacent to my 59. Adjacent and hypotenuse is a cosine. Cosine. I'm going to take the cosine of 59 degrees. And I get the adjacent over hypotenuse. This is like the other problem when it comes to x being in the denominator. The ultimate result is x and cosine of 59 will switch places. So I'm going to write that. X is 5 over cosine of 59 degrees. There's my exact. But let's go ahead and approximate that. And I'm just going to type it in. Take my word for what I get. 5 over cosine of 59, I'm getting 9.7. 9.7 when rounded. This has units, though. It is yards. So we're going to go ahead and write that as well. Do I have to write yards for this? Maybe. Technically, yes. But that's the point of me rounding in a situation like that. It makes more sense for me to just round it. We never say, oh, you're 5 over cosine of 59 yards away. Oh, you're 9.7 yards away. That makes more sense contextually. Part C. X is a leg. 6.5 is the hypotenuse, 6.5 miles. This looks like another cosine situation because 30 degrees is here, x is the adjacent leg, 6.5 is the hypotenuse. So I'll do cosine of 30 degrees equals x over 6.5. There are grounds for me to provide the exact answer as well because I would know how to get to it given it's a 30, 60, 90 triangle, but we'll kind of leave it be. Now, does x switch places with this? No. X is a numerator value. It's divided by 6.5. We got to multiply both sides by 6.5 here. X is going to equal 6.5 times cosine of 30 degrees. And let's go ahead and figure out what the rounded figure is. Cosine of 30. 5.6 about, and this is miles. And I'm good to go there. Now, I want to mention red flags. When I say red flags, I mean things where you say, do I feel like my answer makes sense? For me, do I feel like this answer here makes sense? It makes enough sense. It's less than 6.5. 6.5 is the largest side of this thing. It's the hypotenuse. And 5.6, not too far from it. It shouldn't be too far from it. It's coming off a 30-degree angle. They push pretty close together, so it makes sense as an answer. I trust it. If I got more than 6.5, something went wrong. Maybe I accidentally switched places and I said that, it's cosine of 30 over 6.5. Actually, that would be a very small number. But, you can make mistakes in your calculation and you'll notice when it happens. 9.7, does it make sense that this is 9.7 here? It makes sense that it's more than 5. I'm going off that more so than anything else. Should it be more? Should it be less? Now, neither of these are hypotenuses. So which one should have been bigger? X or 13? Because this one was bigger. X was bigger. X should have been bigger. How come? Because X is opposite the bigger angle. How do I know this is the bigger angle? Because these two got to add to 90. Remember, normally we're used to like a 45, 45, 90, which would be 1 to 1. These would be the same. Well, this is less than 45, so this got to be more than 45. So this is bigger. Opposite the bigger angle should be the longer side. So yes, 16.1 should be more than. So do those answers make sense? They do. Are they right? I hope so. But do they make sense? They do make sense. A red flag can tell you when something's wrong and doesn't tell you how to correct it, but hopefully it kind of lets you go. All right, number 3, let's find the measure of each angle indicated. We'll round to the nearest tenth. They didn't ask us to round to the other ones, and here we are going to round. So we got to find the degrees. Same setup as before. We're going to talk about the trig functions. We have our opposite and adjacent. I want to use tangent of the angle. Tangent of theta equals 4 over 8.1. Whether these could reduce or not, honestly, doesn't matter. We're not going to care about that for this problem. Our calculator is going to help us in some ways. Now, I need to get theta by itself, and that comes by taking the inverse tangent of both sides. I take the inverse tangent here and the inverse tangent here. That is its purpose. You take the inverse tangent of the tangent of something, you are just left with that something, in this case, an angle measure. You take the inverse tangent of a ratio, that's what you get out, an angle measure. So inverse tangent of 4 over 8.1 will tell me what I had to take the tangent of angle-wise to get 4 over 8.1 as a ratio. So if I go to my calculator here, I don't just hit tangent. I would hit tangent after hitting the second button because above that gives me my inverse tangent there. And let's do 4 over 8.1. This is where I said it doesn't matter if you try to reduce a fraction or not. We'll just calculate from there. And that is the degree measure. As long as you're in degrees, that is a degree measure there. And they said round to the nearest tenth, so I'll do 26.3 degrees. 26.3 degrees. That's the angle of that. Just to kind of hit that home, the tangent of 26.3 degrees should be 4 over 8.1. I know this is rounded, but that's what we mean. Part B. We haven't used sine yet. Part B. This theta has 3 adjacent to it, and 4 is the hypotenuse. That sounds like a cosine problem. So in cosine, we'll take the cosine of our theta and get 3 over 4. Sure, it's 0.75, but let's just use the 3 over 4. Theta is the inverse cosine of 3 over 4. Take the inverse cosine of both sides, right? That's what gets theta by itself, and that's what we're going to do. So I'll do that on my own calculator without you looking, and I get 41.4 degrees. These do need that symbol, 41.4 degrees. These are angle measures that we're talking about now. Doesn't matter if this says yards or not, or feet or not. They're still degrees. Not radians, right? You don't know what radians are, and that's okay. You'll learn next year. Part C. Hey, we get to use sine. Theta is this angle that we need to find. Opposite of that and the hypotenuse of that are things that we know. Opposite and hypotenuse use sine. The sine of theta is 4 over 7. So theta is the inverse sine of 4 over 7. What's the inverse sine of 4/7? I don't know. 34.8499. 34.8 degrees. That's us finding angle measures. Angle measures. Using trig. All right. Number 4, find each angle measure to the nearest degree. This is technically easier than the ones we did before, assuming you recognize what the setup of the problem is. Cosine of an angle equals this ratio. It's not written as a fraction. You want it as a fraction? I can do 1736 over 10,000. That'll get you it. Point is, this number is just a ratio of something, some adjacent over hypotenuse. Who cares? Point is, to solve for A, you take the inverse cosine of both sides. Just like before, right? That's what cancels out the cosine portion, and this is where I get an angle measure as a result. So the cosine, so A, that's an angle. This is, in fact, let me say this. Let me say measure of angle A. Measure of angle A equals, and now I do inverse cosine of that. So let's see, inverse cosine of 0.1736. 80 degrees. They said round to the nearest degree. That's it. So 80 degrees for that guy. Part B, we'll do inverse tangent of both sides to get the measure of angle X. Let's do inverse tangent of 1.072. Looking very, it says 46.99, so really close to 47 degrees. Lastly, sine of V, let's do the inverse sine of both sides of 0.9903. Whoops, one of the 9s didn't come up. 0.9903, and I get 82.01, so around 82 degrees. Measure of angle V is around 82 degrees. Do these answers make sense? I'm probably going to be over-speaking for you guys here. You can move along to number 5 if you don't want to hear about this. But do these answers make sense? They do to me. Here's why, and I'm going to start with tangent. I'm going to start with part B. Tangent of an angle is 1.072. 1.072 is very close to 1 as a number. 1 means like something divided by itself. Now, when you think of a 45, 45, 90 triangle, 45, 45, 90, that has the 1 to 1 to root 2 ratio relationship. Well, the tangent of 45, guys, would have been 1 over 1, which is 1, right? If the tangent of 45 degrees is 1, that means that something that is near 1 as a ratio for tangent will be near 45 degrees. 47 degrees is quite near 45 degrees. This makes sense as an answer because my ratio is close to 1. I get that one. It's making sense to me. Do sine and cosine answers make sense? Let's go to part C next on sine. This ratio is also really close to 1, but how does sine work? Sine is opposite over hypotenuse. If I'm dividing something by something else and it's really close to 1, that means my opposite's really close to my hypotenuse. How is that possible? If this over this, if these are pretty close in length together, this angle needs to be pretty big. So being 82 degrees seems to make a lot of sense. If that was 82 degrees, it makes sense that this is close to dividing something almost by itself, but something slightly bigger is the hypotenuse. This being really small in the same vein of having a really big angle also makes a lot of sense. If I had an 80-degree angle here, adjacent over hypotenuse means that this will be a really short leg over a really big hypotenuse in comparison. So to have a small ratio closer to 0 makes a lot of sense to me. So I understand those answers as I get them, as well as, I trust them and all that stuff. This is making sense. All right, let's go to number 5. Angle of elevation versus depression, word problems. That's angle of elevation versus angle of depression. A shark is swimming 28 feet below sea level. If the angle of depression from a boat on the water to the shark is 19 degrees, what is the horizontal distance between the boat and the shark? Okay, so let's draw some water. Don't criticize any of my drawings. Let's draw a shark. Oh no. It's kind of like an airplane with a mouth. All right, let's draw a shark, and we have a boat. All right, so here's the idea. A shark is swimming 28 feet below sea level. Here's sea level. Sea level's horizontal. So there's a right angle that can be made right here. Sea level with shark, and this is 28 feet. The angle of depression from a boat on the water to the shark is 19 degrees. Angle of depression is where you take some horizontal line of sight and you work downward toward it. That's your angle of depression. So for us, we have the boat's angle of depression to the shark being this guy right here. This is the 19 degrees. They want to ask what the horizontal distance is between the boat and the shark. That means, like, how far would the boat have to travel to be directly above the shark? So this is the unknown. Basically, we have a right triangle. If I redraw it one more time, we have a right triangle where this is 19 degrees, this is 28 feet, and this is x. Well, x feet. That one's unknown. That's what we're looking at. All these drawings, whether you're creative with your artistry or not, you need to make sure you know which parts you have represented and what you're trying to find. Once we have our setup, this is like any other problem that we have, as long as we put feet in our answer. Let's use tangent, opposite and adjacent with this one. So the tangent of 19 degrees equals opposite over adjacent, 28 over x. As you've seen before, x switches places with tangent of 19. We get 28 over tangent of 19. And as it's a word problem, I really do want to go ahead and round this guy. I'll go to the nearest tenth, as we've kind of seen before. So 28 over tangent of 19 is 81.3 feet, which makes sense as an answer. If this is 19 degrees, that's going to be the smaller length. This should be a significantly larger length. This is technically 71 degrees right there. If that's how the angle of depression works, that's where we get that setup. That is our answer to this question. Boat would have to travel 81.3 feet to the shark, which isn't very long. That shark is really close. All right. Part B. A helicopter flying 1,600 feet above the ground spots an airplane flying above. Okay. If the horizontal distance between the helicopter and airplane is 3,055 feet and the angle of elevation is 71 degrees, find the airplane's altitude. So here's the thing. The ground, I was going to say the ground doesn't matter. It does matter because they ask about altitude at the very end. Interesting question. So there is ground. All right. The airplane is not on the ground. The helicopter is not on the ground. But I do have a helicopter. Okay, that's a helicopter. All right, I have a helicopter. It's 1,600 feet above the ground. I guess I should have known the ground does matter. 1,600 feet. It spots an airplane flying above. The horizontal distance between the helicopter and an airplane, the horizontal distance here is 3,055 feet. The angle of elevation is 71 degrees. They're saying from the helicopter to the airplane, I think they're saying that this is 71 degrees here. I'm just going to go ahead and do it like that. So this one's interesting for a couple reasons. You might be asking what this part has to do with the trig. It doesn't. This is added height that we need to use at the end of the problem. But the 3,055, I don't want all that to move. The 3,055 is the distance, the horizontal distance between the helicopter and the airplane. There we go. Let's draw an airplane. Let's draw the airplane this way. Okay. And there's a 71 degree angle of elevation from the horizontal line of sight of the helicopter. So that's how these things work. Sometimes they're from sea level and downward, and from ground level and upward, and from a building and whatever. Everything's from horizontal line of sight. What's its angle of elevation? What's its angle of depression? So if someone in the helicopter is looking straight outward and they said, look at that plane, how much angle do they turn up to look to see that plane 71 degrees? This is the right triangle in question. What did they ask? They said find the airplane's altitude. So here's the thing. Let's first find out what this guy is right here. I'll call that x, because inside this right triangle, inside the right triangle, we know this information. We know this information right here. And that's feet, and this is feet. So we'll solve for x first. What do we do after solving for x? Well, then we got to find h. What I'm calling h. We got to find the height, the overall altitude. Maybe a for altitude. But you have to add 1,600 to your final answer. Don't worry about the 1,600 right now. We'll get there. Add 1,600 to your final answer. First, let's deal in this right triangle. So, the curious thing for me, I said there were two interesting things about this problem for me. For one, it's the right triangle that's in midair. The other one is, this is going to be a really big answer. Like, airplanes don't fly this high. I don't even know how high Earth's atmosphere goes. No one has oxygen up there when we see this plane thing. I'm just going to say that right now. Let's see what the answer is. I don't know what it is, but let's figure it out. Tangent. We're going to use tangent again. We have our opposite in x and our adjacent in 3055. We multiply both sides by 3055, and we will get 3055 times the tangent of 71 degrees. Now, this is just the answer of how much higher up in the air the airplane is from the helicopter. After that, we're going to go, and actually, let me just leave that. After that, I'm going to go ahead and take h, my overall height that I need, and I need to add 1600 to that answer. Like I said, I don't want to round early. I don't think the rounding is going to affect anything because it's just addition of an integer. But let's go ahead and just write out what the full answer is going to be here. So I'm going to go to my calculator. I'm going to type 1600 plus 30, and this will be the final answer. 3055 times the tangent of 71 degrees. I don't have an official guess. It might be over 10,000 feet. Yes, 10,472.4. I'm going to round to the nearest tenth. That 0.4, that extra couple inches, you know, it's cutting off your air supply. So this overall height, the altitude of the airplane, which they did say airplane, right? A lot of context in this problem matters. The altitude of the airplane is that high up, which is not realistic for survival, but you know what? They have oxygen masks. I just don't know if planes can actually hit that without incinerating. All right. While standing on top of a hill at a ski resort, Lisa spots the ski lodge below. All right. I got Lisa. Hi. That's hair, by the way. That's hair. All right. Lisa is on top of a hill at a ski resort. If the vertical height of the hill is 1,209 feet and the angle of depression is 53 degrees, what distance must Lisa ski in order to reach the lodge? So here's the lodge. Okay. Now, I'm going to move Lisa a little bit closer to the edge. Careful, Lisa. Oh, she's skiing? Lisa on skis. All right. So the height of... Oh, that's steep. Oh, that's steep. The height of the hill is 1,209 feet. What we're saying is basically if I drew a horizontal through the snow like that and go vertically with the height, this is what I get. You can see where this triangle is going to be. Now, this angle of depression is 53 degrees. Here's where you got to be careful. I'm going to draw this guy right here, which basically represents like Lisa looking down. But this is not 53 degrees. No. The angle of depression is from her horizontal line of sight. So I'm not going from her head, but just from her foot right there. This is the horizontal line of sight. This is 53 degrees downward right there. Now, let's talk about what distance she must ski. That's the hypotenuse. This is her distance she has to ski. This is our x. But 53 is not in this triangle. So how do you find out where to put an angle in this triangle? You have two options. One option. This is technically also a right angle here because that's a horizontal and that's a vertical, which means 53 is complementary with this angle right here. 90 minus 53 is 37, which means if I use this as 37, I could set this up by saying the cosine of 37 degrees equals 1209 over x. That's one setup. Here's the other one. Hopefully this doesn't confuse you too much. This is a horizontal line and this is a horizontal line, which means they are parallel. If those lines are parallel, this can act as a transversal, and alternate interior angles are congruent when two parallel lines are cut by a transversal. What am I getting at? Lisa's angle of depression to the ski lodge is the ski lodge's angle of elevation to Lisa. If that's 53 degrees down, this is 53 degrees up. These are congruent. That means I could use this angle as 53 and take opposite over hypotenuse. I could also do sine. I could do the sine of 53 degrees equals 1209 over x. You have either option. Both are valid. Both will give you the exact same answer. You can either say x equals 1209 times the over the cosine of 37, or x equals 1209 over the sine of 53. How can they be the same answers if these are different numbers? Because these are different trig functions. In fact, if these are both 1209 on top, what this is actually telling you is cosine of 37 and sine of 53 are actually the exact same number. Don't believe me? Let's just type those in. Cosine of 37, sine of 53. Those are just the same number. I mean, it's literally the same thing. So what we're going to do is do 1209 divided by either of those. Let's just, the previous answer, sine of 53, all that. And we get this number here. This is x. This is the hypotenuse. This is how far Lisa has to ski in order to reach the lodge. So x equals 1513.8 feet, or approximately, I should say, equals that. And there is our final result for that one. Go, Lisa. Good luck. That's a very steep descent. Okay. Solve in terms of others. Oh. I haven't done these yet with my students. I'm going to get to these. All right. Let's find the sine of an angle if the tangent of an angle is 4/3. So here's what I like to do for these problems, because people might do these differently. I think I'm going to be in agreement with some other teachers on how we do this. I want to make a right triangle. Now, in this right triangle, because there are, I will mention the other way. You're not going to see me do the other way outside of this. Let's place theta in here somewhere. It's one of your angles, right? The tangent of an angle is 4/3. Okay, so that means tangent of this angle is opposite over adjacent. This could be 4/3. It also could be 8/6. It doesn't matter as long as it's similar with the stuff, right? Because all these things, when I find sine of theta, it's also a ratio of two things. We'll reduce the fraction in the end anyway. But right here, to find the sine of theta, I got to do opposite over hypotenuse. That means I got to find the hypotenuse. This is just unknown, right? So I got to do 3 squared plus 4 squared equals x squared. Now, this is a 3, 4, 5 Pythagorean triple. If you do the work, guys, you're going to get x equals 5. I'll leave it at that. So x equals 5. So, how do we find the sine of theta? Sine of theta is opposite over hypotenuse. That's 4/5. That's the answer. That's the way I'm going to do it. Here's an alternative way. Alternative way is tangent. This is I forget if they call it an identity function or a trig identity. Tangent of an angle is equivalent to taking the sine of an angle over the cosine of an angle. I want to keep moving forward and talking about this. Because if we don't know cosine, then we couldn't do it. I'm going to leave it. I'm going to nip it in the bud. I believe that that's not something that's going to be discussed. I'll leave it. That is a true thing, though, but I'm going to leave it. All right, let's keep moving the way that I just did before. Let's find the cosine of theta if tangent of theta is 3√10/10. Once again, in some right triangle with some theta, if I'm getting 3√10/10 as my opposite over adjacent, my cosine of theta is going to have to be my adjacent over my hypotenuse. So I got to find this guy right here. And it doesn't look like a Pythagorean triple in comparison, especially because that's not a rational set. So 10 squared plus 3√10 squared equals, I'll call it x squared. This is where we get to do one of these practices here. 3 squared is 9. Root 10 squared is 10. 9 times 10 is 90. So x squared is 190. So x is the square root of 190, which to my knowledge and the knowledge of math cannot be simplified any further. We'll leave it as root 190. So this is root 190 here. Cosine of this angle, theta, is adjacent over hypotenuse, 10 over root 190. Rationalized is 10 root 190 over 190. We multiply top and bottom by the square root of 190. That's where we get to. 10 over 190 can simplify because they can both divide by 10. So the cosine of this angle should best be written as 1 root 190 over 19, or just root 190 over 19. And that's the final answer for that guy. Okay. Let's do C. Find tangent of theta if sine of theta is 8/17. I already know the answer. Because it's another Pythagorean triple. So sine of this angle is 8, opposite over hypotenuse, 17. We got to find the tangent of theta. That'll be opposite over adjacent, which means we need to find that adjacent right here. So let's go ahead and find that. That's x squared plus 8 squared is 17 squared. I'm going to save myself the math. Do the math on your own. This is an 8, 15, 17 Pythagorean triple. X is 15. If you know those, that'll really help in what you do. So x is 15. So when we take the tangent of theta, we will get opposite over adjacent, 8 over 15. There we go. Okay. Those are those three parts. All right, that's the end of 9.5. Let's go to 9.6, solving right triangles. Now that we heard everything on Pythagorean theorem and trig and inverse trig and a little bit on these two are complementary, they add to 90, like this is 59 degrees, for example. I already answered one part that I needed. We can do all of this, basically taking everything you heard and go from there. Find all missing sides and angle measures in each triangle. So we found all the angle measures now pretty immediately. Let's just use the 31 to get some of these other answers here. I can use the 31 degree part to with the 14 to get the hypotenuse. I can get that using sine. I'll just call this thing AB. AB. So AB is the hypotenuse here. The sine of 31 degrees equals opposite over hypotenuse, like that. Multiply by AB, divide by sine of 31. AB is 14 over the sine of 31 degrees, which is about, oh, you know. I'll tell you what it's going to be close to. It's going to be close to 28. A little bit less, I think. 14 over sine of 31. 27.18. So 27.2. Mr. Robinson, how did you know this is going to be close to 28? Because this was close to 30, and in a 30, 60, 90 triangle, the hypotenuse would have been twice as long. But it's a little bigger, so that's going to be a little smaller. AC. Now, AC, here's the thing, and here's where I've mentioned something earlier. I could kind of find AC if I use Pythagorean theorem and go like, hey, this squared plus this squared is that squared. But remember, this is a rounded number. I have the exact answer over here in my calculator, but I don't want to keep typing that in. I don't want to write 14 over sine of 31. Use the exact answers you're given only as best as possible, as often as possible. And you have options here. I can work off of the 31 degree angle and the 14 to get this AC using tangent, opposite and adjacent. And that's the one I'm going to begin with, or marry to. So I'll say the tangent of 31 degrees equals 14 over the length of AC. So again, switch places. The AC and tangent of 31 equals 14 over tangent of 31. Now, I expect this answer to be bigger than 14, not just by appearance of the drawing. It's opposite the 59 degree thing. It should be almost root 3 times larger. 14 over tangent of 31 is 23.29, so around 23.3. And that is more than 14, 23.3. So that solves the triangle. Everything's filled out, all three angles, all three sides. Those are rounded to the nearest tenth, and they are used off exact values for that. Now, what I could have also done was I had the 59 degree angle. I could have also used tangent for this, but opposite would have been AC and adjacent 14. It would have been tangent of 59 equals AC over 14. And then AC equals 14 times the tangent of 59. So there's one set. All right, let's go to this one over here. It's a different part. It doesn't have a letter associated with it, though. When I put these in the timestamps, guys, I'm going to call this like part A, part B, things like that, if that works. All right, so this one here, let's go to the side length first. Pythagorean theorem is properly in order. I know all the answers, and I feel like I want to... Are we supposed to... Okay, I'm going to call this out loud first. I already have a short leg of this right triangle that is half the size, that the hypotenuse is double the short leg. Where have you seen that before? In a 30, 60, 90 triangle? That means that this thing is root 3 times larger, which means this is 7 root 3. I got my answers and I'm done. Right? Womp womp. So that would be it. I don't know if that was the goal, if we recognize it, but there we go. We're done. I will be doing this officially, but in doing so... Oh, you know what? We'll still get exact answers. We won't have anything rounded. I'm not going to round square root my calculator if I can simplify it. So, yeah, these are the answers we'll eventually get, just recognizing that 30, 60, 90 was pretty cool, though. All right, so, yeah, start with Pythagorean theorem here. 7 squared plus this BC squared equals 14 squared. So 49 196, and BC squared equals 147. So BC equals the square root of 147. Now, the square root of 147 is 49 times 3. 147 is 49 times 3. So root 147 is root 49 times root 3, or 7 root 3. So there is, once again, revisiting that 7 root 3 that we get. Now, if I want to find A or B, and you can kind of make a choice in where you want to begin. I didn't use cosine in the previous problem, so I'll use it here. Let's find A first. Let's find A. The measure of angle A can be found by using cosine. If I use, now this is also an exact value. I'm comfortable with that, but I'll just use the 7 and 14 that are here. The cosine of angle A is adjacent over hypotenuse 7 over 14. So if I take the inverse cosine of both sides, I'll get that the measure of angle A inverse cosine of 7 over 14, and this is where the calculator is going to have some fun with you, because wrong button, because the inverse cosine of 7 over 14 is, wait for it, 60. So that's an exact answer there. Definitely what we want to see. Measure of angle A is 60 degrees. Right there. Now, measure of angle B, listen, you can use the trig stuff all you want, but how did I find the 59 this last time? I just did 90 minus 31. These two angles are complementary. So once we find one of them, just do 90 minus the other to get that. So 90 minus 60 gets you the 30. So those are the answers that we did get. And again, if you recognize a triangle for what it is as a special right triangle, maybe you can attack it that way. If you did the inverse cosine first, say find A, I think that would have been a good jumping point. Hey, that's 60, so this is 30, and a 30, 60, 90. This is root 3 times bigger. My recognition was a little different than that, but it still worked. All right, we continue 9.6, and I think this is the last page as well. It is. So we're going to solve 4 more sets of right triangles. I might go faster. They still take a while to write. This time we have an angle and a side, and we got to, yeah, and we did this before, but we got to find lengths. Let's do this guy first, AC. We got to use tangent. Tangent of 25 degrees, opposite over adjacent. So AC will be 3 times the tangent of 25 degrees, which is about, 3 times tangent of 25. 1.39, so about 1.4. About 1.4 units there. It should be less than 3. I'm trusting that. Don't use this in Pythagorean theorem to solve unless you use the exact answer that I have right there. That one. So let's just go straight to what we did have. Let's use cosine to get the length of AB. The cosine of 25 degrees is 3 over the length of AB. So AB is 3 over the cosine of 25 degrees, which is about, should be longer than both of those. Not much more than 3. 3.3. 3.3. So 3.3 here. And lastly, measure of angle A. We got to do 90 minus 25 to get that, and that'll be 65 degrees. Not necessarily lastly, but I want to save an easy part for last if we could, and we did. All right, it looks like this should have been a B right here. So next problem, call it part D. We have a hypotenuse with an angle. Yeah, a lot of repetition. It's just good to get some practice in. So a lot of repetition, but this time the hypotenuse is given and we need to find some parts. So let's find this side opposite that. Opposite and hypotenuse is sine. Sine of 51 degrees is the length of BC over 13. So BC is 13 times the sine of 51. Boom, which is about 10.1. Around 10.1. I can use cosine for AC here. Cosine of 51 degrees is AC over 13. So AC is 13 times the cosine of 51 degrees, which is about 8.18 or 8.2. 8.2. And lastly, this angle here is 39 degrees because 51 plus 39 is 90 degrees. Okay, 2 more. Another hypotenuse, kind of very, very similar setup. In fact, we could really work off this pattern. If there's one thing that you want to kind of do in math life is make use of patterns, right? Look for and make use of structure, I think is the way they say that. Express with repeated reasoning. Okay, so this one, right, same things, right? Angle, hypotenuse, boom, boom. Different letters here and there, but if I want to find, say, remember this BC? AC is going to be the same kind of thing. AC is going to be the hypotenuse, how this was 13, this is 15, times the sine of that angle we're talking about, 51, 39. And that's about 9.4. 9.4 for this guy. The BC, like this AC, was the hypotenuse times the cosine of the angle. So BC, in this case, will be 15 times the cosine of this angle, right? It's just the same as the last one when it comes to the appearance of the problem. So 15 times cosine of 39. 11.65, so around 11.7. And lastly, this is the most repeated reasoning. Notice how this was 39 from 51. Well, this is 39, so this must be 51. Obviously, it's a pretty easy calculation, but that's going to be 51 degrees there. And there's another solved triangle. Okay, the very last problem here, we have this angle. This time, this is an opposite, not a hypotenuse. So let's go to work on that one. Let's start with, I'm going to start with sine, excuse me. Let's find this unknown AB. This is the hypotenuse. That's the opposite. So sine of 18 degrees, let's do 14 over x, not x, AB. AB. So again, these switch places here, maybe you're not too comfortable with the switching places thing. You got to show your steps. Please go ahead and do so. I'm making use of my time the way that I choose to. You can pause this and do all the work that you need to if you want to go and check it out. But I want to show you something for the next thing I'm going to find. So this is around 45.3. Makes sense that it's pretty big, actually, because that was an 18-degree angle that we were dealing with. Let me show you another way that I'm going to do this other problem. I think I mentioned it kind of before. You know, if I used, because I'm going to use tangent, but if I did tangent of 18, I'd have 14 over BC. BC would be in the denominator like this. Maybe you don't like the switching places one. Here's what you could do instead. We got to solve the triangle anyway. 90 minus 18 is 72. Let's go ahead and use this one and use tangent with the 72. It's exact. And now AB is the opposite, or BC is the opposite. That's on top. Tangent of 72 is BC over 14. Here's my opposite over adjacent. Now BC is on top instead of on bottom. So if you prefer that for that kind of problem, you can use it. It takes some, I wouldn't say extra work, it takes some extra thought, but it doesn't take extra work. You know why? We needed that 72 anyway. We have to solve the whole triangle. So my final calculation for this entire thing, 14 times the tangent of 72, I am getting 43.08, so 43.1. Very close to, and this makes sense, very close to the 45.3, but still less than being a leg there. That's the final problem. And guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. If you want to check out some more stuff, obviously I've done a lot of things in Chapter 9 when it comes to reviews out of the textbook. I did my own little trig worksheet, my little handmade reviews for sections 9.1 to 9.3. I'm going to follow this one up at some point with a practice test from Chapter 9 as well. Basically versions of what you saw here, but shortened, maybe one type of each problem per thing. And so you can get your calculator ready for that if you want to try. Otherwise, check out the description section down below. Ask me something in the comments if you have any questions for it. Otherwise, take care. I will see you in the next one. I hope you're ready, by the way.